Good afternoon, everyone. Good afternoon, and welcome to the 2025 Don P. Giddens Inaugural Professorial Lecture Series. It's my pleasure to be here with you to honor Dennice Gayme, Professor of Mechanical Engineering with secondary appointments in the Department of Electrical and Computer Engineering and Applied Mathematics and Statistics, and who is also a member of the Ralph O'Connor Sustainable Energy Institute Leadership Council. My name is Ed Schlesinger. For those of you who don't know me, I'm the Benjamin T. Rome Dean of the Whiting School. And these events, this in particular, but these events truly are my favorite events. I think that the traditions of the Academy are an incredible aspect of our profession, of the Academy, and the opportunity to honor someone who has achieved a very senior position in our university and in the Academy in general is something we ought not to take lightly. Dennice's research focuses on the modeling, analysis, and control of spatially distributed and large-scale network systems in applications such as well-bounded, turbulent, and transitional flows. And for those of us who are not control people, that's wind farms and power grids, just lots of rotating windmills. That's the technical term for what she does. Her lab utilizes computational and theoretical methods from applied mathematics, dynamics, controls, optimization, and fluid mechanics. And in her talk this afternoon, she will highlight efforts to leverage the insights gained in the Gayme lab to improve efficiency in the control of wind farms that provide power system services. Now, at this moment, I'd like to take just a minute to recognize one of my predecessors, Don Giddens, for whom this inaugural professorial lecture series is named. Don Giddens was the 5th Dean of Engineering at Johns Hopkins and a professor of mechanical engineering. And with that, it's my pleasure to introduce Grettir Tryggvason, the Charles A. Miller Jr. Distinguished Professor and Head of the Department of Mechanical Engineering here at the Whiting School of Engineering. Grettir.
It is my distinct honor to introduce John Doyle, who is the Jean-Louis Chameau Professor of Control and Dynamical System, Electrical Engineering, and Bioengineering at Caltech. He received his bachelor's and master's from MIT in Electrical Engineering and PhD in Mathematics from UC Berkeley in 1984. His research focuses on mathematical foundations for complex networks with application in biology, technology, medicine, ecology, neuroscience, and multiscale physics that integrates theories from control, computation, communication, optimization, and statistics with emphasis on universal laws and architectures, robustness, efficiency and speed and accuracy trade-offs, adaptability and evolvability, and large-scale systems. His many recognitions include the 1990 IEEE Baker Prize, which is listed in the world top 10 most important papers in mathematics in 1981 to 1993, the 1994 AACC American Control Conference Shuck Award, and the 2004 IEEE Control System Field Awards, and many others. He also has national and world records and championships in various sports, some of which I looked up. It was quite impressive. John, please.
Well, I want to tell you all about Dennice, but that would be 2 hours, and so I'm going to try to keep this short. I've had the most unbelievable students anybody at Caltech has ever had, any of my field has ever had, and even in that group, Dennice really stands out. So I'm going to tell you stuff that you don't know about her. So when she applied to come to Caltech, she was working at Honeywell, which is where I started out. Honeywell was much more important to me than MIT was. And I was working with the best engineers in the aerospace industry, particularly Gunnar Stein, who she worked with at Honeywell, decades later. So when Gunnar doesn't think anybody's smart. When he says Dennice is smart, good. I knew it mattered. Okay. And so she came to Caltech and wanted to do something like completely different. And so, she did a master's at Berkeley where I did my PhD. So, and I knew the people that knew her. So she wanted to do something completely different. So like, what's new and hot? I go, well, maybe wireless. We've got this fabulous guy in wireless, Stephen Lowe. And like, we've all been working on the internet. We're now going to apply stuff to wireless. And she starts working on it. She comes back and goes, this wireless stuff's kind of boring. And I go, yeah, it's kind of boring. She goes like, can I do something a little back more in ME? Do you have any ideas about it? And I said, well, turbulence is kind of a problem they're struggling with. I think we can fix that. And again, we got really lucky because there was a new professor there, Beverly McKeon, who was not so much a theorist, but she was the best turbulence experimentalist. And she loved our ideas. And of course, the theorists hated it. Because, well, if we're right, then they might as well, they have to retool. So anyway, so Dennice wrote this fantastic thesis on shear flow turbulence. And it was a real blockbuster. But what is interesting in the meantime, our wireless guy, Stephen Lowe, decided wireless was boring too. And he starts working on the power grid. So all of a sudden, we now have the best power grid guy in the world sitting, downstream. So she starts working on power with Stephen Lowe. So she ends up working with the guy, the wireless guy, but in power. And that's been a fantastic collaboration. And now she's putting those two together in a unique way. So she's working on the power grid and turbulence in wind farms. And lots of other applications too, but I think that's what we're going to hear about today. So that's a really extraordinary path. And it was thrilling to be part of that, in the small way I was. And it's thrilling to be here to introduce Dennice. Thanks.
Okay, with that introduction, thank you very much, John. I'm going to start talking about a bunch of different things. So I work on spatially distributed network systems, which, if you don't know what that means, these types of systems are everywhere. You see them in wall-bounded turbulence. So, above an aircraft wing in the boundary layer that forms across the wing when the fluid interacts with it. You see it in wind turbine arrays, this famous picture. You can actually see the turbulence based on the atmospheric condition. You get vortical flows off of aircraft. You see it in electric power systems, automated highways, and you see it in terms of what patterns that you see from atmospheric flows. And so systems that evolve over space and time, or these spatially distributed systems, are inherently complex. And they're inherently complex for a lot of different reasons. But one of those reasons is they're often high dimensional. Because say you need a PDE representation, meaning you need math that goes in space and also goes in time. So you get a complicated dimensional system. And they increasingly happen at the interface of nature and engineered systems, where you have to deal with different uncertainties that are coming both from nature and from things that we're trying to deal with and control, such as wind farms. And so the question is, how do we characterize these systems in a manner that enables us to obtain useful models of these systems, models that let us reason about what's happening in these systems, and also efficient control approaches? And so the goal of my lab is to really understand, characterize, and control these complex systems by exploiting structure. And that structure might be physics, it might be some of the interconnections, spatial interconnections in these systems. And I want to do that so I can develop reduced order models of these systems that isolate critical system properties that allow me to reason about more complicated systems by looking at simple interactions. And I want to be able to leverage this new understanding to design performance-enhancing control strategies or operational strategies. And so I've worked on a lot of different systems. From John's introduction, it's all his fault that I work on all of these different things and that I want to work on all these different systems. So I come by it honestly. From wall-bounded turbulence that you see here, all the way to electric power grids. But today I'm just going to focus on 3 problems. I'm going to talk about some of our key contributions in flows transitioning to turbulent, also in wall-bounded turbulence, fully developed turbulence, as well as in control of wind farms. And so I want to start, because many of the audience are not from a fluids community, with just flow over surfaces. So if you think about sort of flow over surfaces, you know, over an aircraft wing, you have this airfoil, and you generally want this flow to be streamlined and laminar. That reduces form drag. That's why cars are designed in ways that look very streamlined. So you reduce form drag, and you can see that. So this is flow over a boundary layer, and you can see this nice streamlined laminar flow that you have here in this region. But as it transitions to turbulence, you get a lot more mixing of this flow. It doesn't look so streamlined and laminar anymore. And what does that mean? It actually means that your flow is mixing up quite a bit, and it's interacting with the surface more. And that's not good in terms of mass transport or efficiency of mass transport across this. So you get less efficient mass transport, and you get more skin friction drag, and you can get more surface heating. So just to make this a little bit more concrete, let's look at an example. And so this is what we call a canonical flow. So these are prototype flow problems that we look at and think about and reason about so that we can understand more complicated systems. So if you think of flow between two infinite parallel plates, and this flow is being driven by the motion of the top plate, so it's a shear-driven flow because you get a shear developing between here. So in a laminar system, you get this nice organized flow that I showed you about, and this is the shear that you get. So in a turbulent flow, everything's mixed up quite a bit, and so then the velocity profile that's coming out of this looks very different. So if you look at the shear in the turbulent flow versus the laminar flow, you're going to look down, and for the same shear on both of these curves, you're going to get a much higher velocity in the laminar flow. And so this is what I mean when I say more efficient transport, because the same amount of forcing, you're going to get much less velocity. The same amount of forcing, you're going to get much less velocity in a turbulent flow. So you have less efficient transport. So if we want to actually prevent this type of thing from happening, because we want more efficient transport in many applications, what we want to maybe do is be able to design some sort of control or model of what's happening in order to design strategies to mitigate this. And so we kind of want to have some sort of plant model. I'm a control theorist at heart, so I like block diagrams. So I want to have this sort of plant model that I can use to design a controller. But unfortunately, turbulence is really, really complicated. John doesn't think so, but in general, most people think turbulence is really, really complicated. And okay, fair enough. So, oh, this is very interesting. Wow, this is going to be very interesting. There's not that much math in the talk, so we'll see how this goes. So we have a flow model, but it's the Navier-Stokes equations. And these models are high dimensional. There's a large range of scales. So you have very small scales close to the surfaces, and you have very large scales. And so that makes it very high dimensional, and it makes it very difficult to simulate or to even do experiments. So these plant dynamics in my nice little control block diagram are kind of hard to analyze and not traditionally super well understood in the context of designing flow control. And so there's a key need to really develop some computationally tractable tools to interrogate what's happening there in order to think about developing new models and new ways to control these types of systems. So that leads me to the first part in terms of the contributions we have, and this is really in transitional flows, so flows as they're moving into the turbulent regime. And so really what we've done here is we've tried to improve the fidelity of some of the tools for efficient analysis. And by doing this, we're using these tools to understand what types of actuation may be beneficial in delaying turbulence and transition. So there's been a lot of work in this area. One of my colleagues, Tamer Zaki, is an expert in this area. And so this is actually a simulation of his. And so you can see this transition. And we've had a lot of great progress from these simulations in understanding transition and turbulent flows. But it's really expensive to do these types of experiments. So this is an experimental transition to turbulence where you can see, again, this order turns into very disordered looking behavior as you move along. And so what we want to do is we want to design tools that have a much lower computational burden or are much more analytically tractable so that we can reduce the number of these very expensive studies like simulations and experiments and really understand which regimes we want to study here. And so one thing that, has proven very beneficial in this regime is just linearizing the things. So, if you don't want to think about this in mathematical terms, I mean throwing away all the terms in the equation that are difficult. So we can just think of nonlinear terms as difficult terms, right? So we can just sort of get rid of those. And it turns out that if you just think about this in terms of, disturbances to the flow, which could be the things we threw away, and this linearized model, the resulting velocities fields we get look really similar to reality. And there's been a lot of progress here. This is actually looking at what's called an impulse response. So when you just hit the flow really hard to see what sort of happens. And so what you see is, what you get from these linearized models is something that looks like this, which looks very much like a turbulent spot that you see in the field. You also get these sort of high and low speed fluid streaks, which is what you're also seeing in these transitional regimes that you see here. So this gives you, a lot of information about what's important and what types of disturbances are likely to make your flow transition. So the key insight that we had in my group, it is really, for my student here, Chung Liu, is that we can actually do better than just a linear approximation by imposing some structure on this nonlinearity, that we can include it in the model in ways that don't greatly add to the computational burden. And so what we actually did is we took this nonlinearity that looks like this, and we approximated it basically using a static gain operator. So we keep the structure here of this nonlinearity. So we just have the same input-output mapping. So this direction only goes to U, this direction only goes to V and W. And so we use this as sort of an input-output gain idea. And so then we can take this nonlinear operator, we can do some manipulations of this block, and we can put it in what very much looks like a robust control formulation. And then we can solve for this static gain as the disturbance that is most amplified here. So the structured singular value, if you will. And so then the largest structured frequency response of this interconnected system gives us the structures that are most likely to induce transition or turbulence. And so where we've applied this is really trying to understand the disturbances that the flow are most sensitive to. And this is useful, say, if you want to design an experiment and you're trying to trigger transition in your experiment, you want the transition to happen as fast as possible. You can reduce your experimental size. Even in a simulation, you want to be able to trigger transition in the most efficient way. So this might be something that you want to do. And so what you want to do then is you want to figure out what initial conditions are going to cause the greatest energy in your flow, right? So this is kind of an input-output response. And you can do this in a lot of ways. People have done exhaustive simulations where they put in all sorts of initial conditions, and they keep testing and testing and testing and testing to see which ones the flow is most sensitive to. As you can imagine, that's quite expensive. You can do optimization with the nonlinear equations. And it turns out you can use the linear equations to do this. And this allows us to do things with input-output gains or norms, input-output norms. So you can use analytical approaches with the linear equations. But the problem is with the linear equations, so again, we're going to look at this plane flow example that I talked about before. With the linear equations, you can do this really fast, almost 0 CPU hours. You can do this on your laptop really easily. You get structures that look like this. So this is span-wise and this is stream-wise. So stream-wise is going in this direction. So these, I got this from you. These structures look like this, right? So these are these long roll-like structures. But it turns out then if you actually do exhaustive simulations or look at sort of a nonlinear optimization problem, the structures look slightly different. They are shorter, so these are infinitely long in extent, but these are sort of oblique waves, and they're fatter. And so if you do exhaustive simulations, they present this data in a slightly different way. But what you're looking at here is you're looking at the structures that are require the least energy density to transition. So that means the ones at the bottom are going to be the ones that the flow is most sensitive to. So here, these streamwise dependent structures correspond to these same things you get from this nonlinear optimization, whereas these streamwise invariant structures, these infinitely long structures, require a little bit more energy. So what we're seeing is these nonlinear approaches give us different answers than our linear approaches, even though we get the insight from it. But it turns out that if we use this sort of structured singular value approach or this structured input-output response, So now again, I'm looking at this in terms of a different space, but what you need to know is this is again span-wise and stream-wise. And so this X here, where you see the red part, which is the most amplified part, corresponds exactly to these type of structures that you get from the nonlinear response. And this point here, which isn't as red, corresponds to what you got from the linear response. So we're getting the correct ordering of these structures, and we're also identifying these oblique, fatter structures as being the ones that are more likely to trigger transition. And so you can look at it again through looking at this exhaustive DNS, and you can see again we're getting the correct ordering of the structures, where the white noise also can trigger transition, but with less energy. The other thing that's nice about this type of approach is we also can reproduce the structures you see in transitional flows and structures you can only see if you use really, 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 really big channels. So this channel is 338 by 770 times the height of the channel. So when I said infinitely long plates, those are really, really long plates, right? So you need to do a simulation this big. So apparently that would take about 1 year to do a DNS or a direct numerical simulation of a channel. And we can do this in probably about an hour on a laptop. And we can identify the angle of these structures that they see in the flow here. So we're reproducing some of the structural features as well. So we've applied this in a number of different configurations. We've looked at stratified flows. So that means the density is changing in the flow. And again, we're matching these type of structures that you see here, and also rotating Couette flow, where you're rotating the flow this way. We're also getting the correct type of structures. And we're sort of moving into thinking about this for more realistic flows like boundary layers, and looking at the effect of different actuation in boundary layers. So I'm going to move around on to the next contribution, which is in fully developed flows. So now we've gotten to the regime where we're completely disordered in this turbulent regime. And here our real contribution has been, again, a modeling framework that enables computationally efficient simulation and analysis of a wide range of flows. And in this work, we're really trying to understand and starting to understand some of the critical interactions between different flow scales that we can, again, use to inform different flow control strategies. So again, I like to use the simplification. I use the linearity to sort of simplify in the structure of the problem through the structure of the nonlinearity in the transition problem. But here we're actually just looking at the flow field and trying to look at structures that people see are ubiquitous in the flow field. And so it turns out, so this is a picture from the Johns Hopkins Turbulent Database. You can see that it's very clear there are these sort of long, streaky structures like I was talking about before in that flow. So if you look head on to this flow, so this is the streamwise direction. So if you look this way, these structures look like this, and you can see these vortical structures here. You have smaller coherent structures in the flow, like these hairpin vortices, which you actually also see on these aircraft wings, where we're just highlighting the contours of vorticity. So you see there's a lot of these coherent motions. And there's been a long history of coherent structures in wall turbulence and trying to understand these coherent structures and building mechanistic models with these coherent structures. What we're going to do is really focus on the particular types of structure I pointed out here, these sort of long, streaky structures, or as Jan would say, the ones that go like this. And there's a lot of analytical, as I said, and experimental importance of this. It also turns out that the momentum transfer associated with that change in the velocity profile from sort of this laminar profile where you have a different angle at the wall associated with the lesser shear. Anyway, you have a greater angle of the wall here, and the skittish friction drag is related to this flow mixing. And so this flow mixing is well captured by these rolls, because as you can imagine, these vortices, you lift up this low-speed fluid near the wall that's not moving, say in a Couette flow, and you bring down the high-speed fluid. So that's the mixing mechanism that you get here, and you capture that, of course, with these streamwise constant vortices as the large scale in your flow. So what we do is we assume that all of the large scales and the mean flow behavior is streamwise constant. And so we think about the flow, we take Navier-Stokes equations, we decompose it so that that's the mean and the large scale, and then we design perturbation dynamics that we simplify, we linearize them in order to look at small scales. So we divide our flow into this large scale, which are these streamwise vortices, and these small scales. And so what we're really doing is we're assuming that the flow is sort of quasi 2D. So we're reducing the Navier-Stokes into a two-dimensional streamwise constant large scale that's interacting with a linearized small scale perturbation field. And so our key observation here is that this large scale structures captures the mean momentum transfer. And if you put in perturbations at the right flow scales, you can get the correct statistics and energetics of what's happening in the flow. And so this is just some example results from this work. So we have a much simpler model. I want to point out that in doing a simulation of this model, it was about 20 times faster than a direct numerical simulation. If you look at the statistics, so this is the mean, and these are sort of the second order statistics, we match very well. And we actually have a quasi 2D flow that only has one dimension in the streamwise direction. So we can solve everything in a two-dimensional instead of a three-dimensional domain, and that's why we get the speed up. And the flow looks actually quite similar to a real flow. And this is just one example at one Reynolds number, but this is true across a range of Reynolds numbers. And so we wanted to apply this model and see if it worked with more complicated flows. So we wanted to look at flow over rough surfaces. One of the reasons that this is interesting is because riblets over these surfaces are a passive form of flow control. So people have heard a lot about, shark skins making things aerodynamic, swimmers and shark skins. There were a lot of controversy about swimsuits with these sort of aerodynamics associated with them. So this is riblet type flow. And so you get these vortical structures forming with the riblets. And then you also see these type of structures in nature. And so we looked at this from the perspective of a very high Reynolds number, so an atmospheric type flow. So we used what's known as a large eddy simulation here. So we reduced the model complexity in that way as well. And so we looked at a surface where you have patches of high roughness and low roughness to model something like this. And we again use a really low dimensional, almost 2D model in order to do this. And what we see is, if you look at these are the patches of the high and the low roughness, the black and the white here. And these are comparisons to other LES that are fully three-dimensional, some experiments, and also a direct numerical simulation. You can see that we're capturing what's happening in the flow and these these secondary motions that are induced by the riblets in this case. So we can also capture that in more detail. So this is looking at a lower Reynolds number where we looked at these what are called blade type riblets over a range of different riblet spacings. Here, this is associated with riblet spacings that cause drag reduction. And you can see that as we start losing some of the drag reduction caused by these surfaces, you can see that we're capturing the differences in the vertical velocity around these riblets with this type of simulation. We've also applied this to passive scalar mixing, and you can see we get, a really complex looking field, even with this very low dimensional model. And so we're starting to bring this together with some of our recent work with my student Lexi here. And so this is where we're looking at a boundary layer flow now, and we're looking at it all the way through transition in a temporally developing boundary layer. So you can see this is in our restricted nonlinear model. We're capturing the development of the turbulence in the boundary layer. So the final thing that I want to talk about is model-based wind farm control. So, I think our key contribution here is really showing that you can improve operational efficiency by doing collective control. And when I say collective control, I really mean control of the flow physics that you see in terms of the interactions between the wind turbines. And so, wind turbines are very complicated because you arrange them into farms and you get wakes. And so you can see the wakes here. So this is a velocity field in a simulation. It's a visualization of a large eddy simulation here. And so the blue parts are the wakes. And you can actually see these wakes forming behind the turbines. Let's see if I can play the movie again. You can actually see the low speed velocity in the particles that are seated here. You can really see the velocity get lower. And then you can see all of the mixing that happens. And in fact, what really happens is as you have this wind coming in, you have turbulence in the atmosphere. It comes into to the turbines. You lose energy you get this wake region, this lower velocity region, and then continuous mixing with the turbulent atmospheric boundary layer is what regenerates the kinetic energy in here. And so if we want to do wind farm control, we really need to account for what's important in the wind farm. And in this case, the structure I really care about in controlling power output in a wind farm is the wakes, because that's going to tell me what the velocity at the hub height is, and that's going to tell me how much power I'm actually going to get out of my turbine. And so I want to look at a particular control application, and I want to look at this because, as John said, I like to connect some of these things to the power grid. And so what I want to look at is secondary frequency regulation, which is when you need to track a power signal. You need to track a power signal in secondary frequency regulation because the grid frequency, the 60 hertz you see on all your plugs and everything, that's associated with keeping a supply and demand balance on the power grid. When you lose that, in order to regain it, because at least historically all of the machines were synchronous and they were still all spinning at 60 hertz, you actually need to track a signal as these machines, start spinning faster and slower to get back up to running all at the same frequency. So that's why I'm tracking a power signal to do frequency control. And so what you need to do frequency control, typically what you do is, in order to track this power signal, you divide your signal into some sort of scheduled bulk power and then some sort of regulation on top of that. And so this type of secondary frequency regulation to get the grid back to synchrony takes somewhere between 30 seconds to tens of minutes. One of the things that's challenging here in terms of a wind farm is that you need to be able to up ramp. So it means you can't be taking the maximum amount of power or maximum kinetic energy out of the wind the whole time, or you won't have the actuation authority to up ramp at a given time. So you need to actually reduce your bulk power supply in order to be able to do this up ramping. And so, you take that and you reduce it by some amount alpha. We call that a derate in terms of the wind turbine. So you derate by some percentage. And ideally, you want to be able to up ramp by more than you have to derate. So with a single turbine, they have to be equal. You can play some tricks with kinetic energy in the rotors and stuff, but I'm not going to talk about any of that. So, they would have to be equal. But it turns out in a wind farm, and sorry, I forgot. There's a direct economic trade-off here. Actually, I'm going to skip that. So in any case, in a wind farm, you can actually take advantage of the fact that these wind turbines are really, really far apart. And so it takes time for the air to travel from one turbine to the next. And you can store kinetic energy by taking energy out later in the farm and not taking it out earlier. So here's an example of that. So if you have two turbines and both are, this one's in the wake of this one, you have some steady state power output. If I turn off the first row of turbines, obviously I lose a lot of power right away. But at a certain point, the second turbine's no longer waked. So if I turn this one back on, for some period of time, I now actually have more power than I did before because both of them are unwaked. And then, of course, in time, it goes back. But you can take advantage of this aerodynamic storage, particularly in really large farms where the inter-turbine travel time can be quite a bit. So, if you take, say, a 200-meter diameter turbine that is 7 diameters apart, two turbines are 7 diameters apart, you're talking about 140 seconds for travel time from one turbine to the next. So if you think of a 10-row farm, you're talking about 24 minutes. And so really, you have about 24 minutes from when your wind hits the front of your farm to when it gets the back. And that allows you to participate in things like frequency markets that have these 30 seconds to tens of minutes in terms of power tracking signals. So the key observation here is that we can improve control efficiency by taking advantage of that. And when I say improve control efficiency, what I mean is I don't have to derate by as much as I want to up ramp. And so the way we do this is we start with a model. And so in our particular model, we want to model the advection of the wake from one turbine to the other. So I'm looking at a very simple model here. So I'm looking at this modeling the farm as a collection of just columns that are one after the other. And then I can model this wake propagation as a linear advection diffusion problem and assume that whatever the incoming velocity field here is the speed that the wakes travel through the farm at. So this is a simplifying assumption. And then I can use some sort of superposition. Here I'm sort of assuming that kinetic energy adds linearly, so I do a squared superposition of the wakes in order to figure out what the velocity at each part of the farm is. And so we can take this type of model and put it in a control framework. So here what I'm doing is I'm going to control a large eddy simulation, like the one I showed you earlier, where the wakes were depicted in blue, using this type of model, where I take into account the travel time, the propagation. And so what we do here is we're using receding horizon control. So that just means we're minimizing the square difference between the signal we want to track and the power output of the farm with a constraint, with a constraint of this wake model. And so we solve the problem for some period of time. We then look at what's happening in the farm and we recompute. So this model predictive control allows us to do some sort of feedback loop by measuring what we're doing. We're going to, as I said, implement this in a large eddy simulation. And we're also going to do some estimation to do feedback. And so what we're going to use is we're going to use an ensemble Kalman filter, and there's a lot of math here. But what we're really doing is we're taking our model and we're running it over and over and over again to get the statistics of what's going on. And then we use the statistics of the model because it is a partial differential equation. It's very high dimensional. We can't actually solve what's going on exactly. So we find the statistics over some number of realizations, and we use the statistics of the model behavior in order to estimate what is happening in the actual wind farm. So we put that all together, and I want to show you that this actually works. So we tested this type of control on the PJM regulation market, which is a power market that operates actually in this region. They have two types of secondary frequency regulation. They have a Reg A, where your signals are kind of smooth, like this, and they have a Reg D market. And they're based on essentially the power imbalance at a given period of time. And so we tested this on 48 different cases, qualification cases, because you have to qualify to participate in these markets, as well as historical signals. And we looked at 3 different wind farm initial conditions, and we looked at D rates of 4% and 6% to achieve power regulation of 8%. So they measure this based on accuracy, delay, precision, and a composite score. So with 4 and 8% in both of these markets, we actually always pass. We do a lot better in the Reg D market, largely because of the way we design the control. That market, everything integrates, all the signals integrate to 0. And so the type of control we're using does better with things that integrate to 0. But we actually do quite well in the other market as well. We do differently in different types of scores. But overall, this means that we can control more efficiently. And so what that means is if we have to only derate by 4% rather than 8%, it means that 4% can be sold in the bulk power market. So if you're a wind farm operator, that means you're not losing as much money to participate in a regulation market. So that's really important in terms of the efficiency and, making this type of control something that you might want to do. And so this is just some sample results to show you what would happen in gray in the wind farm if we didn't do any control, and to show our power tracking under 2 different initial conditions with 2 different D rates. I'm obviously showing the Reg D, which works a lot better than the Reg A, but I'm also showing here some Reg A results. And what's interesting here is, so this is the power and this is the tracking at the top. But if you take a look at the bottom, what you're going to see is the power in the different rows in the wind farm. And what you actually see is we are using the aerodynamic storage that I told you about. So if you look at row 1, what's happening here, you can see, row 1 is taking more power here, but it starts taking less and less power whereas more and more power is then available at the back to do this up-ramping later in the control signal. And you see similar things happening here, where the back row and the second row from the back is doing a lot of the control in order to do that up-ramping. So we really are taking advantage of storing kinetic energy a little bit longer in that flow field so it can be extracted later. So as I said, these dynamic models that are accounting for wake propagation and really the flow physics really can improve efficiency in wind farm control. And it also enables us to participate in these new operational paradigms. Prior to when we first started doing this work, no one was thinking about using wind farms for frequency control, because the idea was we really just wanted to maximize power output all the time, because wind was not a huge player in the energy system. But as it grows to a larger player in the energy system, having these new control paradigms is becoming increasingly important. And so we're expanding this idea of using the structure in the wind farm by using graphs, so we can account for dynamic changes in things like the wind direction. So if our graph looks like this with this wind direction, your graph changes when your wind direction changes, and your graph also changes, say, if you do dynamic yaw, and we can design controllers to account for those things using graph-oriented models that also take into account wake propagation. So as I said, I really am interested in understanding, characterizing, and controlling complex systems by exploiting structure. And so I've highlighted 3 examples where we really try to develop reduced order models that isolate critical interactions in these types of systems, and showed you at the end how we start leveraging some of this new knowledge that we've learned through some of this modeling in order to do performance enhancing control. And with that, I'd just like to thank a bunch of people. So, I had the greatest set of PhD advisors. I mean, between John and Beverly, I really had the dream team. I had someone who was incredibly creative and kind of crazy, like me. My students are saying, like you. And I also had somebody who was extremely disciplined and brilliant and, helped me stay on track in Beverly. So the 2 of them together was just amazing, and just a privilege, especially to be one of Beverly's first PhD students. Bassam, also, I worked very closely with him during all of my PhD. And Charles, who's been my partner since I came here, my research partner and a great friend and mentor to me. So I just wanted to mention him specifically, as well as many, many other collaborators who I've worked with in terms of power grids and wind farms. So these are all my students, former students, current students, and postdocs over the years, without whom none of anything that I do would be possible. So I wanted to mention and thank them. I also wanted to mention all of the faculty and staff in mechanical engineering who, have just been wonderful and welcoming and really do make my life easier every day. That's for you 3 over there, as well as the faculty and staff in Rosie. And this is my current research group. So I just wanted to acknowledge them. They're mostly just sitting right over there. And finally, my family, my husband who's up front, my daughter who I spared you from destroying this entire room, and also my parents, my mom who is here, my dad who is always here with me, because I'm sure they thought I was crazy when I wanted to go do a PhD at Caltech, but they supported me and were always there for me anyway. So thank you.
Dennice, a little bit of insight into the work you've done and the impact it's had. Thank you very, very much. I do want to take a moment to give you a small souvenir of this event. Again, congratulations on this accomplishment, this milestone in your career. And what they say, the college judge the importance of the honored guest by the quality of the food. And so you'll see that we think very highly of it. So thank you all for joining us. Please